We can do much the same with the cubic and quartic equations as we did with the quadratic equations. Suppose we have a cubic equation as the general form of a cubic equation, and let's suppose that that has roots alpha, beta, and gamma. Then ax cubed plus bx squared plus cx plus d must have a factor of x minus alpha and a factor of x minus beta and a factor of x minus gamma. And if we want this to be an identity, true for every value of x, identical expressions, then we have to be careful. We have on the left-hand side ax cubed. On the right-hand side at the moment, we've only got 1x cubed. Well, that's easily corrected. We just put an a in there. Now, it must be an identity. It's got to have factors x minus a, x minus beta, x minus gamma. That's a cubic, and we've got the coefficient of x cubed the same. Well, let's multiply this out. And if this is an identity, we must have the same coefficient of x cubed on each side, which we have. Same coefficient of x squared, that gives us b is minus a times alpha plus beta plus gamma. That gives us that the sum of the roots, which is alpha plus beta plus gamma, is the familiar minus b over a. That's true with every order of equation, cubic, fourth degree, fifth degree, sixth degree, and so on. If we look at x, we will find that the coefficient of x is c on that side, a times alpha plus beta, sorry, not alpha plus beta, alpha times beta plus beta gamma plus gamma alpha. That is called the symmetric product of the roots. And that is alpha beta plus beta gamma plus gamma alpha, and that is c over a. And if we look at the constant term, or the coefficient of x to the naught, we get that d is equal to minus a alpha beta gamma. And so that gives us that the ordinary product of the roots is alpha beta gamma is equal to minus d over a. D over a. Similarly, my favorite word in mathematics, saves an enormous amount of work. Similarly, if we have a fourth degree equation, a to the x to the 4 plus bx cubed plus cx squared plus dx plus e equals 0, and if that has roots alpha, beta, gamma, and delta, we can show in exactly the same way that the sum of the roots, alpha plus beta plus gamma plus delta, is minus b over a. The symmetric product taking 2 at a time is c over a. The symmetric product taking 3 at a time is minus d over a. And the product, alpha, beta, gamma, delta, is e over a. And we could go on and we could do higher degree equations and come out with ever more complicated looking expressions. What I would like to do now is to do a couple of examples which are along the lines of what you did last year. First one is to look at a cubic equation. 2x cubed minus 3x squared plus 4x minus 5 is 0, with roots alpha, beta, and gamma. Find the cubic equation with roots 2 alpha, 2 beta, 2 gamma. Well, I'm going to start doing what you would have done last year. I'm trying to find that, so I need to find, first of all, the sum of the roots. So I've got that alpha plus beta plus gamma is equal to minus b over a. That's minus minus 3. That's 3 over a, which is 2. I get the product, taking 2 at a time, alpha beta plus beta gamma plus gamma alpha is equal to C over A, which is 4 over 2, that's 2. And I get the product is equal to minus D over A, that's minus 5, that's 5 over 2. I could call those roots delta, epsilon, and theta, and I could work out the sum, I could work out the symmetric product, I could work out the product, and then I would be able to write down the equation. That is the technique that you will have learnt last year. I'm going to show you something different. First of all, I want you to notice that alpha is a root, which we have, and that means that if I put alpha into the equation, 2 alpha cubed minus 3 alpha squared plus 4 alpha minus 5, because alpha is a root, I know that that is 0. Right, now here is the little trick which works with these. Let's put big X equal to 2 times little x. X, not alpha. We're doubling all the roots, and so that is basically reflecting that. That means that little x is big X over 2. If we now substitute that in the equation at the top of the page, we will get 2 big X over 2 cubed minus 3 big X over 2 squared plus 4 big X over 2 minus 5 equals 0. So that is another equation. Well, let's see if we can notice what the roots are for this equation. You might be ahead of me, might. What happens if I put x equal to 2 alpha? Try big X equals 2 alpha. The left-hand side now is going to be 2 times 2 alpha over 2 cubed minus 3 times 2 alpha over 2 squared plus 4 times 2 alpha over 2 minus 5 equals 0. Well, that, if we just divide 2 by 2, which is 1, or it used to be, we get 2 alpha cubed. Sorry, I should not have said equals 0. The left-hand side is just equal to this expression. That's all. The left-hand side equals the blue bit. And the blue bit equals the bit which is now coming out in purple. Minus 3 alpha squared plus 4 alpha minus 5. Now, if we look at the red bit, we find that 2 alpha cubed minus 3 alpha squared plus 4 alpha minus 5 is 0. It's what I wanted it to be on the line before. I was ahead of myself. So this now tells us that if we put 2 alpha into this equation, we get 0. So 2 alpha is a root of that equation. Let's call that equation 1. So 2 alpha is a root of equation 1. My favorite word coming up again. Similarly, 2 beta, 2 gamma are roots of 1. So my new equation is 2 times x over 2 cubed minus 3 times x over 2 squared plus 4 times x over 2 minus 5 is 0. And if we just multiply both sides of that by 4, we will get x cubed minus, multiplying by 4, 3x squared, multiplying by 4 plus 8x, multiplied by 4 minus 20. So there is the new equation, which has roots 2 alpha, 2 beta, and 2 gamma. it saved some work. It would have saved much more work if I had been looking for a new equation with roots 2 alpha minus 3, 2 beta minus 3, 2 gamma minus 3. As long as I do exactly the same thing to each root, this new trick will work. You put big X equal to 2x minus 3. That gives you little x is big X plus 3 over 2. Put that in the original equation, simplify everything with your algebra, and you will then have the equation which has roots. Oi, I've lost it. You will then have the equation which has roots 2 alpha minus 3, 2 beta minus 3, and 2 gamma minus 3. Any equation will come out with that nice little trick. Here's another one. We have a 4th degree equation with roots alpha, beta, gamma, and delta. Find the quartic equation with roots 1 over alpha, 1 over beta, 1 over gamma, and 1 over delta. Well, if you start thinking of the technique you had last year, some of the roots would be 1 over alpha plus 1 over beta plus 1 over gamma plus 1 over delta. Then we would want to simplify that. We've got to find it all in terms of, it's a big mess. But with the new method, it's really rather nice. If you put, you're doing the same thing to each root. You're taking the reciprocal. So if you put big X equal to 1 over X, then little x is 1 over big X, and you get, putting it in the top equation, I'll call it equation 2 because we've already had equation 1. If you put that in equation 2, you get 3 times 1 over x to the 4 minus 2 times 1 over x cubed plus 5 times 1 over x squared minus 7 times 1 over x plus 2. Now we know, I'm not going to do this in detail, we know that alpha is a root of this equation. So 3 times alpha to the 4 minus 2 alpha cubed plus 5 alpha squared minus 7 alpha plus 2 is equal to 0. If I put big X equal to 1 over alpha, if I put big X equal to 1 over alpha, then alpha is 1 over x. And so this becomes, the left-hand side is 3 alpha to the 4 minus 2 alpha cubed plus 5 alpha squared minus 7 alpha plus 2, which we know is 0. We know that x equals 1 over alpha is a root, and similarly 1 over beta, 1 over gamma, 1 over delta, and so we can get rid of that. The equation we want, we've got. We multiply by x to the 4, and you get 3 minus 2x plus 5x squared minus 7x cubed plus 2x to the 4 equals 0, has roots 1 over alpha, 1 over beta, 1 over gamma, 1 over delta. You will find some notes and the opportunity to do some nice, more interesting questions, I think. They're ones I set anyway, so they're bound to be more interesting. If you look in the website, you'll find the links to them.